In this video, we're going to talk about the average value of a function. So if we have a set of values, say y1 to yn, then the mean, or the average of those values, you know how to do that. You just add up the values, divide by how many there are. Now, we're going to try to do this for an arbitrary function over an interval. So we know that from other applications that we've been doing, we like to set things up as Riemann sums and then take a limit that gives us a definite integral. So in this case, just writing this as a summation notation, I've got the values y1 to yn, so I've got the sum from I equals 1 to n of y sub I, and then I can think about pulling the 1 over n out. All right, so let's now extend this to a function over an interval. So we're going to approach this like we've done with the volume problems that we've done before. We'll take the interval from a to b, cut it up into n subintervals, and for simplicity's sake, we'll make them all have the same width, and choose a sample point in the ith subinterval. So now I want to take this sample point, I'm going to plug it into the function, do that for each of the sample points that we have, and we can find the mean of those values, just like what we talked about above. Add them up, divide by how many there are. Here's the summation notation for that expression on the left-hand side. This kind of looks like a Riemann sum. I've got the summation of a function evaluated at sample points. What I don't have is the delta x here on the right-hand side. So let's see if we can get delta x involved. Take the interval from a to b. We divide it into n subintervals. We know how to calculate delta x. It's b minus a over n. Solve that for 1 over n. Just divide both sides by b minus a. Gives us an expression to substitute now for 1 over n. Going back to our summation that we had on the previous slide, take out the 1 over n, put in 1 over b minus a times delta x. Pull that out in front, and I really do see now a Riemann sum here. So then if we take the n as limit as n goes to infinity, we get the average value is defined as 1 over b minus a times the integral from a to b of f of x dx. So there's our formula for average value. Let's do a couple of examples and show some graphs of what's going on here. Let's say we want to do the average value of f of x equals x on the interval from 0 to 1. You could probably guess what this average value is just based on the fact that we're using x from 0 to 1. Okay, you can probably figure out what the average is going to be. Well, let's see if actually going through the definition and calculating it agrees with our intuition. So in this case, a is 0, b is 1, f of x is x. Take an antiderivative, plug in the endpoints, we get a half, which makes sense here, right? Because if f of x is just x, the average value here from 0 to 1, the average of that would be a half, if you would. And graphically here, you kind of see that if here is the average value, I see that basically everything that's up here is mirrored by something that's down here, so on average they would average out to a half. So let's do another example here of f of x equals x squared. Interval is 0 to 2. Again, using our formula, a is 0, b is 2, f of x is x squared. Antiderivative, plug in the endpoints. So we get 4/3 in this case. So here's a graph here. Here is our average value here, this horizontal line. You can see, and think about this in terms of an integral perspective. If I think about it, I move this 2 to the other side, 2 times the average value would give you the area of this rectangle here, right? Because the width of that rectangle would be 2. It would be the integral from 0 to 2 of x squared. That would be the area under the curve. So the area of this rectangle here is the same as the area under the curve here. So just give you a little bit of an idea of graphical interpretation of what the average value means.